Hey guys, welcome back. This is the 2026 Chemistry FRQ question number 2. Let's get started. Number 2, answer the following question about the chromate ion and the dichromate ion. Um, let's see. I'm kind of guessing maybe this might be redox, maybe not, but let's see. All right, so I'm kind of taking out my redox hat. I'm gonna leave it on the side to see if I'm gonna put that on. And if you don't know what I'm talking about, listen to part one video about putting hats on. Part A, the bonds between chromium and oxygen in chromium can be represented as covalent bonds. No kidding. One possible Lewis diagram for a chromium ion is shown in figure 1. Based on Vesper theory, predict the molecular geometry of the chromate ion. Wow, are they easy this year? All right, so what is it? Well, guys, it's four um, bonding domains, right, about a central atom. So what is that? That's a text, and then on top of that, it's actually four identical species, which means that it's a perfect tetrahedral, right? So it's a tetrahedral. So I'm not even gonna. Well, actually, no, I guess I should address it. Don't be a snob, Mr. Kim. All right, fine, let's go. So I'm gonna go. Boy, this is a long question. Holy smokes! All right, let's get prepared for this. Yeah, this is a lot. This is a long one. All right, so let's go to two. Question two. Hello, can I write? It won't let me write. What's going on? Um, two. Oh, there we go. What is this? Um, question two, part A, Roman numeral one, right? All right. So it says, what is it? You'll say, it didn't even ask you to justify, right? The geometry will be tetrahedral. Right? I mean, they could have at least asked octahedral, right? No, no octahedral, no seesaw, I think, no T-shape, I think either, right? In AP. All right, moving on. Let's go. That's 2A, 1. So, let's go to 2A, 1, 2. Right? No, 2A, 2, right? So this is done. On figure 2, draw a complete Lewis diagram for the resonance structure of a chromate ion that results in a formal charge of 0 on two of the oxygen atoms and a formal charge of 1 on the other two oxygen atoms. All right. So now we gotta dust up what formal charge is, right? So this is where when I used to teach AP, my equation was very different than the ones you found on the internet, but I simplified it. What is formal charge? Formal charge is calculated as, at least in my classes, right? I would say it's the total number of the valence electrons, right? Minus the quantity of the lone pair electrons, right? Plus the bonding pair electrons divided by 2. This is terrible. This looks terrible. Sorry. Let's do that again. Electron is here. That's a plus symbol, and it's that. So that's what it should be, right? And remember, for formal charges, we want to try to bring it as close to 0 as possible. But here, what they're asking you to do is try to figure out an alternate, right? Probably, possibly not the correct one, right? So let's take a few seconds and look at this one up here and see what the formal charge is, right? All the oxygens have the same formal charge, right? Because they're all identical in this case. So let's take a look. So to calculate the formal charge up here, right? It would be total valence electrons. You know, oxygen has 6 valence electrons. If you didn't know that, boy, God help you, right? Minus, let's look at lone pairs. In the diagram that we see here, how many lone pairs we got? We got one, two. 3. So we got lone pair. The total, now remember, in my equation, I said lone pair electrons, not lone pairs. So therefore, the total number of electrons in a lone pair is 6. All right. And then to it, how many bonding pairs we got? We got a bonding pair here, right? And which is a lone pair here. And we got how many in a bonding pair? Each bond is 2 electrons, right? So it's divided by 2. So that gives us 6 minus 6 plus 1, which is 7, which gives you total formal charge of -1 on all of the oxygens and in this diagram. So that's kind of not cool, right? So let's go over here. All right, so let's try to figure this one out, right? Um, they want total charge of 0 on 2 of the oxygen atoms. Well, look at the equation, kids, right? We know that this value right here is never going to change because that's the total number of valence electrons in an oxygen atom. That's always going to be a 6, right? So in order for us to get a formal charge of 0, right? So let's bring us back over here. For formal charge equals 0, that would require this other portion here to be equal to a 6, right? So then that means that we would expect the expression lone pair electron plus bonding pair electron divided by 2 to be, in this case, 6. That'll give us a value of 0. How do you do that? Well, let's take a look. Lone pair electron. So if you go back to the original one, what do we notice, right? So we want the 0, right? And that's -1. So how do we change that up? We want then this value to go down, right? And this value to go up. So that means that, let's think about it for a second. We want, oh, no, that's not what I'm talking about. We want this value to go up, this value to go down, right? So what is that talking about? That's talking about we want the lone pairs to go down. Lone pairs to go down and bonding pairs to go up. Hello, did you just hear what I said? You want the lone pairs to go down, which means you want one of the dots on the outside here to disappear, and you want more bonding pairs. So isn't that what this is, right? So let's think about that for a second. So let's just draw it that way, right? So if we put a double bond here, and then instead of the I will erase it, but we do one of these where you do a coordinate covalent bond, right? So those 2 electrons are promoted to bonding pairs, right? Then you get one of these. The actual way to draw it, right? Not that AP is going to care. If you're in college, and if you're in one of my chem classes at NYU, I would have ripped you out if you wrote it anyway but this. But there it is. So that's how you draw it, okay? All right, so let's do the formal charge calculation here. And here, what do we got going? To do the formal charge calculation, we got lone pairs, right? Over here, now the lone pair is 4, right? And then plus, what is bonding pair? You got double bond, which means that there's a total of 4 electrons in the bonding pair, divided by 2, right? That gives us 4 plus 2, which gives us 6. And remember, this value is being subtracted from our valence electrons. Therefore, in this case, formal charge would be 6 minus 6, which is 0. So this does give us the formal charge. They want 2 of the oxygens to do that, and we'll do it this way, like so, right? And then what else? They said they want the formal charge of -1 on the other 2 atoms, right? Well, we already calculated here. What do they look like? They're single bonds, right? So therefore, we just go back here, and what we do is we maintained the original formulation, and we got one of these. Now, just double check, right? I'm gonna count off, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 pairs times 2 is 32 electrons, right? And just go back to the original one. We got 1, 2, 3, 4. 4 times 4 is 16, which is 32 pairs of electrons. So this diagram is correct. The total number of valence electrons depicted in the formula is still 32, and it's showing that. And if you're thinking, oh, wait, Mr. Chromium has more than octet. Yeah, Okay. Let's leave regions chem and understand that yes, atoms can have um different types of hybridization, right? Can you say D2sp3, right? No, whatever. All right, so this is correct. Okay. All right, so moving on. We're done. And just to remind the graders, I'm just gonna go here and put 2A, 2C diagram. Okay. All right, so let's go. We got a lot to do here. Man, this is so long, right? All right, so 2A, 1 and 2 is done. Let's go to 2B. All right, 2B. When reacted with strong acid like HNO3, chromate can be converted to dichromate and water in a reversible reaction. Write a balanced net ionic equation for the reaction between chromate and strong acid. Well, I'm gonna assume that you guys are wearing big boy, big girl chemistry pants, right? Which means you already know that what do we know about nitric acid? It's the acid of choice for cleaning glassware, right? If you were in my class, if you were one of my APs, yes, you would know. It's the acid of choice. Why? Because any product that nitric acid reacts with is going to be a nitrate-based product, and the solubility of nitrate is fully soluble. So what? What does that got to do with this question? This has to do with this question in that nitrate is going to be soluble. And anybody who's super soluble, they're going to be spectators, right? So therefore, that's immediately taken out, right? So which really means in the end, we're going to have this, this, and water, right? And that's what we're going to draw. So for part 2B1, let's go. Part 2B1, part 2B1, part 2B1. Don't forget what I was saying. My gosh. Oh man, I'm going to forget what I just said. Um, is there an end to this? Where's the beginning? Where's the beginning? Oh, wow. So we're going to go to 2B. Uh, 2B, I completely forgot what this is. 2B, Roman numeral 1, right? Yes. It says net ionic equation. Hello, get out of here. Wait, no. Share. I hope we're recording. No, yeah, we're recording. All right, good. So what do we got? We got uh, nitric acid, and you know that nitric acid is going to be dissociating into protons, right? Because it's fully soluble. It's a strong acid. That is going to react with our chromate, not dichromate, sorry. 2 minus, and that's aqueous for us, right? And it said it's going to convert it into our dichromate plus water. All right. You're thinking, what are you thinking? What I'm thinking? I'm thinking, oh my God, do I need to do balancing redox, half reactions, adding protons and water and all that? Just hold on. Before we do that, let's just see if we can just mass balance this. You got protons. You got one proton on the left side, one on the right side. But let's go take care of our non H's and O's, right? So therefore, we get chromium. So I'm going to have to put 2 chromiums on this side to balance the chromiums. All right. So the singleton that I have is actually proton on the left side, isn't it? So I'm gonna take care of the oxygen first. So let's look at the oxygen. You got total of 8 oxygens on the left side of the reaction, and on the right side you got 7 on the dichromate and then 1 in the water. That's 8. Hey, oxygen's balanced, right? Which means we only have to mass balance the protons, and in which case you got 2 H's on the right side. So therefore you put 2 on the left side, and I think we're balanced, right? So double check that everything is balanced and we're good to go. This is our net ionic equation. All right, so let's go back here. So that's done. Is the reaction redox reaction? Oh boy, didn't we just say that? Oxidation number of chromium. Oh, they just, that's so much hint. They might as well just tell you, right? that it's a yes or no. All right, so let's look at part two. They want to know if it's a redox. All right, in order to assess the redox, so what do we got going? I'm gonna leave a blank up here. I'm gonna say, okay, chromium in CrO4 2 minus. What is that? That's gonna be oxygen is minus 2 times 4, that's minus 8, right? But that's gonna be neutralized, all but minus 2. So therefore, chromium must be plus 6. Has oxidation state of plus 6. Chromium in dichromate, Cr2O7, 2 minus. Let's take a look, right? Oxygen is once again minus 2, right? Times 7 is minus 14. And all of it except for 2 gets negated or neutralized. So that's going to be positive 12 from the chromium team. There's 2 of them, and 12 divided by 2 plus 6 again. So Cr and Cr2O7 is also plus 6 oxidation state. Since there is no change in oxidation numbers, there is no transfer of electrons, right? So you would say, I said, well, is the redox reaction? I say no and oh. This is not a redox reaction, right? So again, if you don't understand what I'm doing, when I used to teach AP Chem, I used to tell kids, leave a blank and write the final answer first, and then go your reasoning so that when the AP reader's reading, you hit them with the correct answer first, and then you do your explanation. So in case you're dumb and you don't know how to explain it and you explain it wrong, maybe they'll gloss over it. Okay, but it's correct in this case. All right, so let's go to let's mark that off, right? So two hello. Part 2B2 is done. It's not a redox reaction. So at this point, maybe I'm going to put away my redox hat, right? And then just focus on something else. The following information applies to part C and D. In acidic solutions, dichromate reacts to form chromium trioxide. No, that's not it. Chromium 3 oxide, sorry, according to equation 1. Chromium 3 oxide, no, it's not chromium 3. What the hell is that? It's not important. I know it, but I just want to be a better person. CrO3 would be what? Let's see, there'll be minus 2, 6, right? It's chromium 6, right? Duh. Chromium 6 oxide. Anyway, it doesn't matter. All right, CrO3 can be electrolyzed to plate objects with thin layer of chromium metal according to the equation. All right, so let's look at the equation. So you got Cr2O3 plus 6 protons plus 6 electrons, giving you solid chromium and water. And here we go. We see one of these, which means now we also need to switch our hats, right? So we're looking at total cell potentials, right? So maybe not put away the redox hat yet. Part C. Is the reaction represented by equation 2 thermodynamically favorable or unfavorable under standard conditions? All right, so what are we talking about? I was just going to say delta G, but they even told you just about your answer to calculate delta G. Like, could they actually tell you any more information, right, to help you with this question? Show the work that leads to an answer. So we need to calculate delta G. So most of my students, when I used to teach class, I used to tell them they're supposed to memorize it. But if you didn't, we're going to have to go to the videotape. So what is a videotape? That's your reference table. And I'm not used to this reference table because I stopped teaching AP last year. So therefore, this table is totally new to me. I do notice there's actually one extra sheet. So they gave me more info. All right, so let's go to delta G. Where's delta G? Delta G, where are you at? Did I just shoot through that? Oh, no, there it is, delta G. All right, here we go. Right, so we got delta G right here. And now delta G, there's a couple of different renditions I need to use. Well, we're going to use this one, right? NFV, right? Let's go. So it says reaction. So you got to calculate delta G. So let's do it. So we got to calculate delta G. I'm gonna, you know what I'm gonna do? I'm gonna pause the video for a second. I'm gonna bring up this test in my other computer so that I actually have it, so I don't have to try to scroll on video so much. All right, so I have it in here. So let's just go. Um, yeah. So this is just trash having to scroll through this. All right, so let's go to two part C. Right. So two. Come on, work with me here. Part C. Okay, part C has no Roman numeral one or two. So we got to calculate this, right? So it says they want to know. So I'm going to leave a blank again so I can put the correct answer. I'm going to calculate for delta G. So let's do it. So we got delta G, and the equation that we looked at is negative NFE, right? Like that. All right, so what are these? These are um, N is mole of electrons, right? And where do we get that? We go to the original equation, right? I'm not going to scroll, but if you go to equation number 2, you see 6 electrons on the left side of the equation. That tells you that 6 electrons or 6 moles of electrons are going through per reaction. So 6 moles of electron is N. What in the world is F? F is Faraday's constant, right? So if you don't know Faraday's constant, I tell my students that you're supposed to memorize that. But if you don't know, it's right here somewhere, right? Right here, right? 96,485. So it's going to be 96,485, right? It's going to be 96,485. And what is that? That's going to be coulombs per mole of electrons, right? So that's going to be coulombs per mole of electron, right? And what is delta, not delta, what is E? E in this case is in the problem. So if you go back to equation number 2, which I'm not going to scroll to, the value that I circled, right? Remember I circled the potential. It was negative 1.32. Okay. That's it. It's this easy. And then now what you do is you calculate delta G. And let me grab a calculator here. And I get a positive. This does not look right. Yeah, because I mistyped. Okay, hold on. 6 times 96,485 times 1.32. That's better. All right. So what happens? You got a negative value for your potential, and you got a negative on the equation. So therefore, the total value is going to be positive, right? Now you can already tell that we solved it, and you could have done this without it, but I think it says calculation of delta G. That's why we're doing this, right? So the total delta G is 764,161.2 is what I got. That's kilojoules, right, per mole. So what? Um, it's positive, right? Be careful, right? Delta G is either positive or negative. You don't have a signless delta G, right? So you would say, is the reaction thermodynamically favorable? I would say the reaction is unfavorable, favorable, because delta G is greater than 0. Right? Remember, Gibbs free law says that no, Gibbs free energy says, not Gibbs free law. Gibbs free energy says reaction is spontaneous if delta G is negative, right? And that's it. That's 2C. All right. I am going to scroll here so we can read together. I just didn't want to scroll over and over while we're solving it. Okay, so this was done. Let's go to D. Calculate the number of grams of chromium that could be plated onto the surface of a steel rod when 15.0 amps of current is applied for 30 to 50 seconds. Right? I don't know if you learned this in your class, but I used to tell my students that when you see the concept of an amp, right? What is amp? Amp is coulombs per second, right? That's much more useful for chemistry. For physics, amp is fine, but for chemistry, coulombs per second, right? All right, show the work. And then so they want to know number of grams of chromium that could be plated. So we're gonna come up with the grams in the end. All right, so let's go ahead and do this. All right, so this is 2D. All right, so let's go to 2D. All right, so how do we solve this? Well, you got your um, amps, right? What's amps? That's um, that's current, right? What's a symbol for current? I know when I teach the physics class, I tell them current is I, but for the AP kids, you should also learn that, current is I, right? So if you go here, current is I, right? So what's the equation, right? I usually make my kids just memorize Q equals it, right? Q is it. But if you didn't memorize it, it's here somewhere, right? I equals QT. Remember that translates to Q is it, right? So what I will do is here, you understand that Q is it, right? And what does that mean? Our current was 15.0 amps, right? 15.0 amps. 15.0 amps. Amps is coulombs per second times. What was the number of seconds in the problem? Let me look here. 3250 seconds. 3250 seconds. All right, so that gives us a value. And once again, you can just do this as one single shot dimensional analysis. But again, right, who's that weird, right? I did know this one weird kid, my first year teaching here for AP Chem. Every one of his work was actually the world's longest dimensional analysis. All right, what do we got? We got coulombs, right? So that's our charge, right? It's our charge. We get 48,750 coulombs. I'm not going to worry about the sig figs right now because we're not there yet. They want to know the number of grams of chromium, right? So we want to know how to convert this into a mole. Well, we do have that. It's Faraday. Remember Faraday? So we know that it's 48,750 coulombs. And if you divide by Faraday, that's going to give you the answer, right? Which is, what is Faraday? Faraday is, what's the value? 96,485, right? You should memorize that. Or at least I guess you're watching this video this year. You've already taken it. So you're like, you don't have to memorize it. You're going to forget it. 96,485. What is that? That's coulombs per 1 mole of electrons, right? So what does that come out to? So 48,750 divided by 96,485. That is 0.505. Should I worry about sig figs here? Maybe. Let's go to 3 sig figs, right? Because 15.0 amps and 3250 is both 3. 3 sig figs will be 0.505. So 0.505 moles of electrons is what we got. We're not done though, right? So now what we need is we need equation 2, right? So I hope you have the equation in front of your face because I have it here, right? Also, so I don't have to scroll back. But let me explain to you now what's going on. So now it's just stoic, right? So you got 0.505 mole of electron, and you want to go from mole of electron to mole of our um, chromium, right? Cr? Yes, chromium, right? So now, dang it, I'm gonna jump over. I will jump to the equation because I don't want to do it, but if you go to equation 2, what do we got? You see here, the stoichiometric ratio is 6 moles of electron to 1 mole of chromium. All right. I guess I didn't have to scroll, but that's okay. So we got, oh, hello. 6 moles of electron to 1 mole of chromium. That's from the equation. And then what do we need? We need the molar mass of chromium, and it's, where is it? Oh, here it is. So if you go to molar mass, I don't know what that is. Chromium is what? Uh-oh, my computer's not liking it. Man, I would hate to redo this. 52. 52.00, right? Please, computer, work with me. Uh-oh. I'm going to pause for a second. Oh, no. I said I'm going to pause for a second and came back. All right, so that's what I need to do. I need to threaten to restart this computer. All right. Ooh, we're not happy. My computer's not happy. All right, so 52, right? We stop zooming in. I'm not touching anything. All right, times, right? All right, so let's take a look, right? We got moles of electron cancel each other. We got moles of chromium, so you need moles of chromium here, grams of chromium here, and we said it's 52.00 grams per mole, right? That's it. That should give us the total amount of chromium that can be plated. So it's going to be 0.505 divided by 6 times 52 gives me 4 point, how many sig figs? 3 sig figs. So therefore 4.38. 4.38 grams of CR. All right. So I'm going to write, it's asking what, how many uh, number of grams of could be plated, right? So we would say 4.38 grams of chromium will be plated. Okay, good. 2D is done, right? Check. Let's go on. This is like a never-ending question, isn't it? Part E, in a separate experiment, an iron wire is placed directly in a solution of half molar dichromate with a pH of 1.99. All right, so a couple of notes here, right? I'm going to write down, this is acid, right? What else we need to know? Well, you can write it out, right? It's iron, solid, plus dichromate, Cr2O7, 2 minus. And then what else? It's in an acidic solution. I'm guessing it's going to be like this, right? Something like that. Do we need to do that? You don't, but I'm just kind of translating stuff into chemistry. The concentration of dichromate remaining is recorded over time, and the results are presented in figure 3. What are we looking at? We got this and that. Explain how the data in figure 3 supports conclusion that the reaction is first order. Oh, here we go. Now we're at rate laws, right? Um, First order with respect to dichromate. So I'm gonna spend some time and kind of talk about the what it is, right? So we got rate order, right? And they want first order, right? What do we know? There are two types of rate orders, right? First is what? Differential rate law. And you got your integrated rate law, right? All right, so what's the deal here? In differential rate law, what are we looking at? If you change in the first order, respectively, right? How do we know? In differential rate law, what do we know? We know that if you increase the concentration twice, it results in the increasing of the rate twice, right? And in this case, it's probably not the case because I know there's concentration here, but it's concentration versus time, right? And if you've been a pretty decent AP chemistry student, that's when you should have been remembering that when we're talking time, we're talking about integrated rate law, right? Because that's what integration is, right? In this case. So, what's the deal with, so then that's out. We're not thinking about that right now, right? So let's go to the integrated rate law. And integrated rate law, what are we looking at? We're looking at for first order rate law, right? I told my students that you should memorize this, right? But I don't know, maybe you guys did, maybe you guys didn't, but all general chemistry students, right, including college chemistry, like when I used to teach general chem at NYU, you're expected to memorize these, right? So if you're going to go to NYU or any other mediocre school like that, you should know, right? Or if you go to better school than NYU, then of course you should know, right? So the equation that I use is this, is going to be concentration of A naught over A sub T is equal to negative KT, okay? But if you didn't memorize it, and you're regretting life decisions, that's okay because you can have it here. I hate switching over because my computer's freaking out, but rate laws are here. Here we go, right? And what do we got? That's your first order, right? And what's this? This is your second order, right? And this is your half-life for first order, right? Because you guys AP students are too delicate to be, figuring it out on their own. So we are given this to us, right? And what happened? Why does this look different than the one that I wrote? Because, if I guess, I don't want to call it calculus, but I guess if you do understand some calculus, right, you understand that equation translates to that, right? Right? It's the same thing. Well, you can use this. It doesn't matter. It'll come out the same. Okay? Come out exactly the same. All right, so what? The other thing you need to understand is in order to tell if it's a first order integrated rate law, we would actually have to take the value and we'd have to look at something else. We would see that's important. So we look at graph of the line A, right? Dot, 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 versus T, right? Is it straight? So if you look at the natural log of the concentrations over time, you should see a straight line. If you do, that's a first order rate law, right? So how do we do this? There's a couple of ways to do this, right? Now let me just go back to a second. Explain how the data in figure 3 supports the conclusion of the reaction. So essentially what we have to do is something like this, right? Um, Maybe I'll do the work in the problem because I want to kind of show some work. So this is 2E, right? So I think I have enough space here, right? So, you know what? I'm going to go to the next page, right? So let's look at 2E. So looking at 2E, right? I'm going to leave like two blanks so I can write a sentence, right? But let's start doing some work, right? So I'm going to create a chart, right? The chart is going to be, what are we looking at? We got time and we got your concentration of our dichromate, but I'm not going to put it here because I want to be able to visualize a little bit better. So I'm going to skip it here and I'm going to do this, right? If I do that, and then what I'm going to look at is here is going to be the natural log or the line like that, right? Now, what do we got going? I'm not going to do the entire graph, right? So I'm just going to look at a couple of things. So I hope you have your graph in front of you, all right? Because I'm not going to flip back. So I'm going to take 3 data points, right? We know that time, we're going to start at 0, right? And then we're going to look at time 48. That's the maximum on the time axis. And half of 48 is conveniently 24, right? So that's the middle part that I'm going to look at, right? So now what? We have the data for the concentration, don't we, right? So at time 0, concentration of dichromate is 0.50. Where did I get this? I got it from the figure 3, right? I'm reading the graph, folks. You go to 48, and what do we got? We got 1.0, I'm sorry, 0.10, all right? And then I'm gonna go to time 24 at 24 minutes. Oh, that one is in the middle somewhere. Um all right, let me show you. So much for not scrolling, right? All right, so let's go. So the graph, the chart I was making is right at time zero, remember it's point 0.50, and at time 48, I got a point 0.1, and that's what I wrote in that chart that I made, right? Right. Now at 24, what do we got going? 24 is here, and we know that's 20 here. I'm sorry, a point 20 and point 25. So point 0.21, point 0.22, point 0.23, point 0.24. So I'm going to call it point 0.22, 0.22 at 24. Okay. So let's go. So I'm going to go here, 0.22. All right. This is why I should not be scrolling so much. Sorry. If you're getting motion sickness, I don't know. 22. Take some Dramamine, right? No, don't take Dramamine. I'm not telling you to take medicine. All right, so I was just kidding. Anyway, so moving on. So when you look at that, what do we know? We got to take the natural log. So if I go line point 0.5, I get negative 0.7. If I go line point 0.1, natural log of, oh, sorry, natural log of zero point 0.1 gives you negative 2.3. All right. And then you got your natural log of 0.22, and it gives you negative 1.54. Okay. All right. Um, I don't know if you're a weird person that is really good with math and you can actually see graphs, you could actually skip all this, all right? But let's take a look. What we want to look at is this, right? The relationship of those values. If that's a linear value, then that's it. Then this is a first order, right? There's two ways to do this. You could actually sketch it out, right, on the side. So you can sketch it out and do that. But for me, God gave us what equation for slope in what middle school, elementary school. I forget when I learned it, right? So use that here, right? So what's going on? So we got your rise over run, right? Rise over run. So this is your x coordinate. This is your y coordinate. So just figure it out that way. So what I'm going to do is I'm going to take the slope of the first point to the last point and get the slope of the entire graph of the ln versus t. And then take another slope between, I guess, 0 to halfway point. And if the two slopes match, that means the line is straight, right? So let's go. So slope of 0 to 48, right? Time-wise, what does that come out to? 0 to 48, that's going to be rise over run. That's going to be y2, which is negative 2.3, minus negative 0.7 all over 48 point minus 0, right? Let me quickly grab my calculator and come up with that. It's negative 2.3 plus 0.7 divided by 48. I get negative 0.03. Okay. So that's my slope. So I know we didn't plot this, but that would be the slope if we were to graph this. So now I'm going to take a slope of time goes from 0 to halfway point, which is what, 24, and let's see what the slope of that line is. Now, what do we got? We got negative 1.54 minus negative 0.7 all over 24 minus 0, right? So calculator again, negative 1.54 plus 0.7, negative 1.54 plus 0.7 divided by 24. And what do I get? I get negative 0.035, right? I might have punched in something wrong. So I'm a little bit off, but nevertheless, what do we know? That slope is almost exactly the same, right? So now I'm confident that the graph of uh, natural log right, of dichromate ion concentration over T is going to be linear. Okay. So what I would say is, the question says, explain how the data in figure 3 support the conclusion that reaction is first order. So it's not asking if it's first order, right? So you're going to say that the reaction is first order, right? Is first order because the graph of the natural log of CR207 2 minus versus time is linear. By the way, this is where I'm gonna tell you, if you are like dying because it's taking too long, I might even skip 2E and just write here without any of the explanation, just write reaction is first order because graph of natural log of blah blah is linear. Because if you really think about this, right? Look at this, guys. They already gave you this, they told you this is first order, right? It's not asking you to find it. It's telling you it is first order. Tell us how you know. In that case, all this calculation or, all this charting I did, it's not really necessary. So you could actually get away with this entire question 2E by just writing reaction is for first order because the graph of the natural log of dichromate ion concentration versus T is linear. If you write that, you could have skipped all this and you would probably still get full credit for this. Okay. All right. So moving on. 2E is done. Um, 2E is done. And actually, on retrospect, I would just default to that definition of integrated rate law, right? And just be done with it. Following information applies to parts F and G. The student creates a plot of net. Oh my God, they have it on the next one. God, that's so stupid, right? I guess we could have just even looked over the next one. Although the time is different. That's okay. Student creates a plot of natural log of CR207 2 minus versus time for trial with an initial concentration of this as shown. So they give you a half molar concentration initially. Calculate the value of the rate constant K for the reaction. Report your answer in units of minutes over. Oh my God, they actually gave you the units. They used to not do that also, and they used just to take you off on a minute. Hey, anyone taking chemistry in college next year? They don't do this. You have to figure it out. Okay. All right. So here we go. So how do we solve this? We go back to the equation that we had before, right? I'm just going to use the one that I normally have my students use, which is ln, right, is equal to a naught over a sub t equals negative kt. Or you can use the one from the reference table. Whether you do that or not, it's gonna still work the same. It's the same equation. Okay. All right. So now what? Calculate the value of the rate constant. Let's get some information here. Do we have a naught? Do we have a naught? Yes, we do. We have negative. Where are we at? Did they give us the values? No, you have to figure it out, right? All right. So, oh no, but we have this, right? So at 0, at 0.5, right, from the other problem, right? From the other problem, what do we got? I already did this, right? Negative 0.7 or 68, right? Yeah. Okay. All right. So, you know what? I'm just gonna start plating, as they say in restaurants. I'm gonna start plating for service. Let's do it. 2F. Let's do this. All right. So the equation that we need, right? We're going to calculate the rate constant K, right? I'm going to leave that here, fill it in later. So the equation that we need is going to be natural log of A naught over A sub T is equal to negative KT, right? Now, through some algebraic magic, what do we end up with? We can solve for K, which is going to be what? The natural log of A naught again. That's A initial, right? Sub AT all over. negative t, right? Don't forget the negative, right? There's a negative here. Okay, now we can start plugging some values. K is equal to, what is A naught? So I guess I do have to go look it up, right? I'm just going to read it from here, okay? So what do we got? We got, you know what? I'll go. I want to explain it to you. So A naught is going to be at time zero, right? So this is A naught, right? At A naught, what are you going to end up with is going to be here. It's going to be just between 6 and 8, but it's just closer to 6. So I'm going to call this negative 0.68. Okay. And then what are they asking us to do? Calculate for the reaction. So then therefore, time t could be 18, right? So if we do that, what do we got? This is at a sub t or a sub 18, right? And what's the value? Value here is between 1.2 and 1.4, almost exactly in the middle. So I'm going to call this negative 1.3. Okay, so remember these two numbers, right? So this would be a sub t is equal to that, and this would be equal to a naught. That's the value we need. And it's 18 minutes, right? So let's go back to our equation, right? And start filling these out. So we got your natural log. Stop moving. Okay, natural log of what do we got? A naught. That was negative 0.68, right? And at our T18, which is a sub t, we got negative 1.30, right? And all divided by what was our time? Time one was 18 minutes. Okay. So plugging this into a calculator, line quantity of negative 0.68 divided by negative 1.3, right? And then you divide that by negative 18, you get a positive value of 0. Now, how many sig figs? Let's stick with 2 because 0.68. So I'm going to go 0.036. So it's going to be 0.036, right? And what's the unit? Unit is, it's first order, right? You really should memorize that. For first order is 1 over time, right? And that's your answer, right? So you'd say K is equal to 0.036, 1 over minute, and that's your answer. Okay, that's it. That's part F. Oh, I hope this doesn't go into like H, whatever. That's F is done. F is done. Where's F? Let's go. F is done. G. Student then runs a second trial experiment under identical conditions, but uses an initial concentration of quarter molar dichromate instead of the half molar dichromate. On figure 4, carefully draw the plot in of line dichromate concentration versus time that would be expected for the second experiment. The point at time 0 has already been plotted. Well, thank you very much. That was really stupid. You know, they didn't have to do that. We could have figured that out. It's just simply what? Natural log of 0.25, right? Anyway, so yeah, there's a lot of hand holding in this exam, I noticed. And then not to mention, this is really stupid because wait, this is so easy because think about this, right? It's first order rate law, which means that as long as the equation, the reaction that and the chemistry doesn't change, the rate doesn't change. It's a first order rate law. So therefore, what do you expect? Now, in this in the integrated rate law, right? The slope of the graph is what, guys? Right? In the first order rate law, slope of k is your rate, right? So therefore, you don't expect anything to change. So really, in the end, in this case, what happens? Same chemistry, same equation, same reaction, right? Half the concentration. What happens? That means the starting point is going to change, which they already gave to us anyway. So I don't even understand the point of this question, which is the slope is going to be identical, right? So what's going on? The slope, according to the original dotted one, is It's moving approximately one box in the Y directions for every two boxes, right? So I'm going to go every two boxes, I'm going to go one box down. Every two boxes, one box down, every two box down. So my new graph is going to probably look like this. And that's it. So there it is, right? And then since I did it here, I'm going to go here and say on the 2G, C diagram, right? Or I should have put figure 4, but whatever, figure 4. Okay. And that is the conclusion of the most painfully long question, which was question number 2, and hopefully it'll get shorter from now on. Thank you for watching and staying tuned, and I'll see you on the next one.